Yes, we will be talking about oh no, it works. Again, no, using maps. Oh, SOM as was initially invented by a Finnish scientist, Kohonen. So, and so another name for this type of neural network is called Kohonen maps. Well, this uh, type of neural networks was biologically inspired by a functionality of cortex. So, which is about clustering together the areas or the populations of neurons being responsible or being activated for similar inputs. Uh, in other words, this functionality is also called topographic mapping. So, and the idea is that so um, you have an audio signal, for example. So it is processed by one part of the brain, and a visual input is processed by neurons in a different part of the brain, and then they are obviously interconnected for complex cognitive abilities. But this is a principle of topographic mapping. And SOM follows this principle. So it has topographically so in its core it has topographically arranged neurons. So basically, SOM principle. So you have your neurons. So this uh, which are arranged in a reasonable topology. So what do I mean? So there is a clearly pronounced connections between uh, geographically close neurons. So those are kind of real lateral. And so these connections, they are also expressed by the arrangements of weight patterns. So there is another dimension here which is not shown. So I mean, you can think of it as a tensor if you wish. Um, so which is a set of weights. So basically, if you zoom in into a neuron, so it's a neuron with many input connections. So that is a receptive field to certain phenomena. So all of them characterized by weights. And they also have kind of explicit connections to communication channels, so to say, to other neurons. And here I have to be to make myself clear. So this is a biological inspiration. So we are not talking about plausibility, and these are two different concepts, obviously. So there is a biological inspiration. So basically, it's a mathematical abstraction of functionality observed in nature, versus trying to exactly recreate or emulate the processes in biological systems, which is biological plausibility. For example, spiky neural networks, they're biologically plausible to large extent. This is biologically inspired, rather. So but nevertheless, so again, so for us to understand the functionality, so here we have communication channels, kind of. To neighboring neurons. And then we have this receptive field, so which is characterized by weight. And the important thing is that all these neurons, so they are um, connected to sensory, equally connected to sensory system. So you have your sensory system, which is essentially your feature vector. Of certain dimensionality. It can be low dimensionality if we talk about low. You will work with this zoo data set, which is low dimensional data set. Iris is low dimensional. MNeast is rather high dimensional already. But the important of dimensionality D. So we have the D features over here. And each of the features is actually connected to all the neurons in our population. So basically the size of this other dimension of self-organized maps is D. So we have D vector, D weights over there. And the idea is of this algorithm is that so now we have this living neurons that tries actively to attract patterns, similar patterns to themselves, and they want to they will even compete with each other. So there is a great deal of communication between neurons, so that eventually they you start seeing some patterns emerging on this topology. Yes. In normal neural networks, you have that they are layer after layer after layer that they go through. Is this like we have just one layer that takes everything in and then organizes itself? Mm-hmm. Okay. Yeah, yeah. So it's a single layer with it's kind of even subclass of recurrent connections but it's you see it's a special class. It's not random recurring connections. So so each neuron is connected. So it has a notion of proximity.
So if I'm a neuron, I can be connected to like 10 neighbors if we have that as a constraint, or just for like cardinal directors.
Yeah, so that's a good observation. So yeah, you can put it in this way. So you can decide how many neighbors you want to have, or you impose a regular structure, topographic structure, so a lattice. And in this case, each neuron it has at most 4 neighbors, above, below, left, right. But the communication mechanism allows you to reach certain number of neighbors, and that we will control algorithmically. So how far we can reach.
Is 4 a fixed number, or can it be like, is 4 a fixed number?
It is fixed number for the chosen topology, which is lattice. It can be, in the simplest case, it can be a line. So you can build self-organizing maps on a line. You can build a self-organizing map on a torus. So I mean, there are different attempts. All of them are good. At the end, they are really good data visualizers. Yes.
Is it better to build it like a lattice or like a torus? Like, do we gain something from having a different structure? Like, is a line worth it? Because
you see, I mean, I'm kind of afraid to give a very shallow answer to this. At the end, what you do here, you do projection of complex manifold onto a certain regular structure. Some manifolds, some surfaces, multidimensional surfaces, are being displayed sufficiently well on regular structures. Some maybe you can get better insights when they are kind of twisted in this fancy manner. So, but it's like trying different.
Depends on the cost.
Yes. Moreover, so I will mention. So already now I can say that one of the limitations of this approach is exactly the static structure. So you already limited. So this is your hyperparameter, how many nodes and it's also one of the bottlenecks of this architecture. So there are variants of self-organizing maps that kind of grow the structure. So you start with it's like in a fractal, if you wish, in a fractal-like manner. So you start with an atomic structure, say a single node with few neighbors, and then you define a threshold. I mean, when you say that okay, this current topology is not expressive enough, and expressiveness in terms of as you will see, discrimination of patterns with respect to chosen similarity measure. And at a certain point, you say, well, this 4 nodes is not sufficient. Let me introduce some more nodes onto this structure. And in this way, so at the end, you obtain a well, it's still a plane, but not of a regular size. So you kind of let it grow into different directions. And in this case, in general case, you can allow more than 2 dimensions to grow. So and then it would somehow you will have more degrees of freedom to place your patterns on the surface. But again, more than 3 dimensions is already hard to visualize. But at the same time, maybe it's still would serve a purpose for in classification mode. And by the way, talking about this, so now it naturally brings us to the following topic. So SOM belongs to a class of unsupervised learning algorithms. So it's unsupervised. Algorithm. And then another taxonomy which is important is it belongs to a class of competitive learning. Which is opposite to error correcting learning. And what do I mean is that at the end, so let me visualize. Maybe you already did it in lab 4. So we have a map, and this here in the intersections we have our neurons, many of them. Etc. And the idea, as I said, we want to implement a competitive learning so that each neuron tries to attract a certain pattern with respect to some discriminative function, as we will see. So it will attract patterns I here, pattern pattern J here, etc. But again, being an unsupervised learning means that the data is unlabeled. And as such, I mean, what you have, you again, by the result of training, you have just a data structure. So, I mean, you cannot do much. But then, I mean, any unsupervised algorithm you can turn into supervised if you know the labels. And then you do the extra pass by on the train on this trained structure, checking what labels hit specific regions. So, for example, here you have L1, L1, L10, L8, L1, L8, L8, L8. So you do it kind of post-training, and what you can do, you can basically assign to each of the neurons a label by the majority vote. And in this case, so when you did assign it, so it's like yet another dimension of of a neuron. So now you label it with so it becomes like this famous grandmother cell or whatever. You can use the structure in classification mode. So you give a new sample, like new data feature vector. And then, so the network will attract it to a certain region. And then, so you check basically the result of the majority vote and say, this is pattern label 8. And when you've done it, then you can even color. So now so these labels can be used for coloring the map. So and then I mean the visualization effect emerges basically. But that is in principle done by all visualization techniques like T-SNE and such. What else? What is self-organizing maps? Again, so to remove this mysticism with neural nets and such, it was formally demonstrated that it's a nonlinear version of principal component analysis. So you reduce dimensionality, so drastically reduce from n features to 2 dimensions only. But coming back to this comment of yours, initial one, so about the number of neighbors and the specific topology to consider. So probably from the visualization point of view, it doesn't make sense to go to some 4-dimensional case where each node may have like many neighbors. But from the classification point of view, it might make sense because you would develop certain kind of clouds on your 4-dimensional space where specific labels will hit. And the algorithm is generic in this case. But you need to define, you will see, you need to modify this distance function. Shall I take a break? Yeah, let's take a short break. So we back in 5 minutes. Or as soon as I see that all people are back.
Och sen din tanke med det. Station och kunskap och situationen.
Det här, jag såg för demonstration. Det finns en artikel som beskriver det systemet. Men det som de gjorde så de extraherade konstnärliga GPT. Scenario. Och de använder att kommunicera videon som matchar en beskrivning mot objekt som man ser på exempel. Så det är så att det visar ju visual resonance inom autism.
Använder du
det är någonting som är
eller bygger du en egen
jag tror att jag använder
jag har hört vissa
som sagt det är lite komplext. Jag vet inte, det är svårt att men det är säkert man kan inte
jag vet inte om de vill ha trajectoryn också.
Jo,
lite stort tillräckligt intresse.
Jag vill ha det samtidigt som den
någonting.
Ja, jag tror att det är så.
Vi har gjort animeringar
i gränsområdet.
sedan som plottar trajectoryn efteråt. Men jag kan plottra trajectoryn samtidigt.
Jag tror att jag plottrar den som innan så körde animeringen på.
Jo, det sker också för att de måste ha någon spel.
Ja, exakt. Jag skulle inte låta så. Ja, det kan man göra.
Ja, jo, det är bra mappar.
Ja, det kan vi vara tillsammans. Det ska vi jag låter det till en sida. Mycket mer som man ska planera så. Det är inte viktigt.
Det är nog så att man uppgraderar mappar. Sant. Svårt att se det.
Ja, men det-
vad jag menar. Så. Ja.
Ja. Shall we continue? So what I will do first, I will sketch the kind of present a high-level description of the algorithm, and then we go into some specific technical details. So some algorithm. Three phases. Initialization, competition, and cooperation. Initialization, this is quite a typical step for all kind of fit for neural architectures. So you initialize all weights to small random numbers. The essential part for the competition phase or requirement is that each neuron is equipped with a so-called discriminant function. And this discriminant function will take input pattern, the feature vector as an input pattern, and compute the score, and then we will use the neuron with the smallest value as the winning neuron. So let's call it FD. The smallest FD is winning. Also, it is called as best matching unit, or BMU, BMU for short.
So if we have one neuron that respond like one to the feature vector that will, if we say that would give us zero, it's the best neuron to that specific vector. And then I assume it tries to collect everybody that has as low or the lowest number, because you said they are self-organizing, so they try to collect.
Yeah, so here again a good comment. So it's about a high level understanding of the functionality. So here we will assume kind of centralized view, so that we will we will, I mean, for each input pattern we will compute this discriminant function, the distance basically of the pattern to the vector to the weight vector, and then we take the minimum so of all the results from all the neurons, and that will be our best match. And then, but then we come to this second part of your question. So about what to do with this information. So the third phase is this cooperation. We will have a procedure. So again, so if we have our lattice like this, and say that we scored, I mean, for some pattern I. So we chose this neuron. So we want to be able to kind of spread this information somehow in a certain neighborhood. So affected or excited. Oh, these are not nodes, neurons. Frankly speaking, I have don't have machine learning background from the beginning, and this term neuron. So to me somehow it has always this biological incline, and in the case of neural networks, artificial neural networks, I prefer to still think about these guys over here as computational units. So they are like microcomputers just doing simple computations. That's, I mean, they inspired by functionality of groups of neurons. That's a different thing. But I mean, that's why I sometimes kind of automatically write not neurons, but something else like nodes, computing nodes. But seriously, I mean, I remember I had a class, so that was quite a long time ago. So when was it? 94. It was like my first year at the university, 94. And we had a class on on neural networks. So they existed back then as well. So, but somehow I had this internal conflict when I heard neurons. So I didn't like biology much. So I mean, and it just created a block for me to follow the algorithmic part. But okay, that's my problem. Yeah, so but we will have a group of neurons that will be excited by this pattern and in this phase, in the cooperation phase. And this is the winner um, that determines this neighborhood. Again, so now knowing the background from spiky neural networks, Hebbian rules, so that there is nothing weird in this step. So I mean, we do have this principle that certain neurons tend to yes.
Do the winning neuron or node change the discrimination function of the neighbors?
Not the discrimination function, but the weights.
Okay.
So it will affect the weights.
So they become more similar to itself.
Exactly. Yeah, and as, already now you can imagine how it works in what way it is self-organized. So pattern. So there will be discriminative function. I mean, in the case of standard SOM, it's a Euclidean norm. Euclidean distance, sorry. So you have a weight vector, you have, and then you have, set of vectors randomly initiated. So the first choice is really random. So I mean, placement of a certain pattern. But then, so this winning node, initially a random winning node, will create an attraction field around it. Distributing this weight to the neighbors. So yes.
What if we give it like 10 examples of L1 at first, or also we give it the same pattern multiple times, wouldn't that like to color the entire map? Or give it another?
It's a good question. It really, I mean, the answer to this question is the hyperparameters that we have. So it's part of the hyperparameter, how far away you spread this information. So yes, in the kind of trivial case, it will be a map for a single pattern, of course. Yes.
Are the neurons and nodes able to become exactly alike? Or do we have
No, no. So there is a mechanism, and now we are going directly into this thing, so which prevents them from being so. So technical details. So discriminant function, so FD, so. In classical SOM, Kohonen maps, it's L2 distance. In the implementation, sometimes you see the square variant of it, so you remove this computation of square root, but it's so f of d of x. So that's your input vector is sum d I equal 1 xi minus wi square. So xi is the input pattern coordinate of input feature vector, and wi is the weight of a particular node, and this is a distance. And so the result of so you basically compute argmin to determine the index of the winning node. So again, so let us see a very simple grid. So if this is our best matching unit, so it has index I. Or let's put it I. So I is an index of best matching unit, and of course it has coordinates in a given lattice. And the thing is that now what for the next step is essential that we should introduce a notion of proximity, topological proximity of nodes from here to here. So let's call it Sij. So basically distance Ij. So and here we come to this first hyperparameter that's set of hyperparameters that actually doesn't allow for a single pattern to occupy the entire space. So controlling neighborhood. Let me first just write it down as a formula, and then I will show you the part of the code. So G, so that's that will be your coefficient is E, so exponent minus Sij square divided by 2 sigma square. So this sigma over here, this is a parameter controlling this the size of the neighborhood. So your neighborhood will is a decaying function of the distance from the chosen node, and G controls G is the coefficient that actually determines to which extent G is part of the neighborhood. So this S first S. So we compute this distance from node I to say BMU. So from all nodes on the topology to our scored one. And again, so this is a Euclidean distance, which is I minus x I minus x BMU squared plus y I minus y BMU. So where x and y are actually x and y coordinates of your topology. So you compute. So if this is your BMU, and this is I, so that this is I. So this is xi. This is x BMU, etc. And and here we come to this decay. So that's a pretty much standard exponential decay. You can meet it in different technologies. So when you compute, when you want to introduce some decreasing in time function, so exponential decay is a pretty much standard way to define it. So sigma t. I will explain it now. So it's some initial sigma 0 E minus T divided by tau sigma. So what again? So just to actually, it's not a rocket science. What this formula tells is that our parameter that controls the width of the neighborhood is a function of iterations. So on each iteration, so we will we need to have a possibility to adjust. So how aggressive we are. So in the beginning, we can be quite aggressive, but then we probably want to be a little bit more careful about updating the weights of others. And that's what this formula tells. So sigma 0 is some initial hyperparameter. T is the iterator. And tau is the parameter how fast you decay the rate. So now I can probably quickly switch to my Jupyter. So, and this is the code from Lab 4, obviously. And I just want to bring your attention to this cell that just models the behavior of this function. Anton, please come. So don't wait outside. So basically, it is. So let me see. This function sigma and a computation. Well, not sigma, the whole G. So you are interested in the computing coefficient that you will use to reduce the amount of change in weights. So here is a simple example. So for here, this distance array, so each element, so it's a 3x3 lattice of distances. So one indicates, I mean, it's my own distance. And then, well, it could be easily be 0, but and then, so neighboring nodes to the left to the right and below have distance 2, and so on diagonals distance 3, and in the lower row distance 4. And that's what you get. Yes, so this is the result of computation. So and that means that so the best matching unit will have the reduction coefficient 1. So I mean, actually, you will update the weights as they are, and then the farther away from this best matching unit, you will have different reduction coefficients. So which become smaller and smaller. And yes.
So we can see it like I'm affecting my right neighbor with
87%. Yes, and yeah, exactly.
And then
exactly. Yes, and that this tau sigma is the hyperparameter that actually controls how fast you decay. So in some trivial cases, or so you can set it such that the entire map will be just spanned by a single, so no chance for other patterns to. Yes.
I assume it's not possible for the effect to be 1. I can be 1, but I can't expect another one to do 1. It means 99.9.
No, exactly. Yes. So and that's why. So this strategy, this update strategy, is also known as winner takes all. So if I'm hit by a certain pattern, so only me is the center of gravity, and the rest are well, will have smaller effects. So basically, now the only thing is which is left is the adaptation phase of SOM. And here we come to the formula for the weight updates. So we will update, we will compute the weight update. So basically, your delta W is, so remember, so there is a one-to-one correspondence between the weights that you weights of the neurons that you have and the input patterns. So and as such, so you can see feature vector as activations, neural activations as well. So you take your pattern. You subtract it from your weight vector. And then what you do, you apply the reduction, the coefficients. So you apply coefficient G. So this is neighborhood reduction. And then you also have a learning rate. And this controls, this is an extra reduction coefficient, which even affects how aggressively I change, I adjust my own weights. And the learning rate follows the same principle as of exponential decay. So with every iteration. So it starts with some initial value, and then it changes. So it becomes less aggressive as you perform iteration. So this is the iteration. So basically, and this now concludes the technical specification of SOM, and so hyperparameters are then sigma 0, so initial neighborhood constant, the the decay rate after with iterations, so tau sigma, initial learning rate, and tau learning rate. And as you see, so now so certain patterns will tend to be located in a certain place, and then the neighborhood, actually the width of the neighborhood also will reflect the proximity, so the overlap with other patterns, because I mean the less decay you have, so the more focused your neuron will be. So at the end, you can set this parameter so that a single neuron will react on one pattern, or the kind of. But what you want to see, you want to see a smooth transition between patterns all over the topology that you have. Yes.
I assume you don't optic every node or neurons at the same time? Because if we have like a very large map and I'm activated in the corner, and the opposite corner is so far away that I don't really affect it. Do I calculate any new things for that? Because it should, in theory, also lose its decay rate for new learning as we progress to a new step.
Yeah, and normally you choose the decay the rate such that initially you still I mean with your update you cover the entire map. So it's not that I mean part of the maps become random. In this case, you will have isolated islands. That's what you will see. So you still want to update. I mean, you start. I mean, this brings us to another question about the way how to train stuff. I mean, neural networks. I mean, one of the tendencies is to supply like batches of the same label, which is not always the optimal strategy. So the network become biased and that's not biologically plausible at all because we used to more kind of stochastic learning. So you need to kind of as a general rule, so you need to shuffle your data before input into any ML algorithm, basically. And in this case, you will prevent this situation that your network will become kind of dominated by a single pattern. So, yes.
If we go back to how the lattice is formed, like if we have a 5-point lattice, like we have up, north, south, east, and west, and then we also have like northwest, so I connect to another neighbor. I assume that would affect our learning. Do you know? Because it would mean that I can spread like northwest as fast as I can spread north and south. If the lattice is instead of just cross, that we have a cross and diagonal vector.
Yeah.
Because that wouldn't that affect how the neighborhood looks?
But you see, your neighborhood, I mean, what you say is probably will have a different realization in terms of the equation on how you define this G, because this is the G that actually controls. I mean, you don't go to the left to the right, so you just compute for the entire map G for each node. So and in this assuming a lattice structure, it's a concentric area that you cover. And as I said, so initially you choose it such to even if you hit the say the corner, so that you still should cover the entire map until the far opposite corner.
So the connection between the nodes are representative of how I affect them. Like
only by means of this reduction constant. So and that's what I implicitly kind of mentioned in the beginning. So consider it as a communication channel, so on which you propagate this G. So it's not that. I mean, you can also look at it as a kind of connection strength that you adjust. But then it becomes, to me, it becomes kind of cumbersome because in this case, you need to have you need to have synapses from each node to all other nodes, and then you kind of have different weights on them. So basically, the far right node is connected to the lowest left by synapse with a very low weight. So I again I don't dare to say that it's kind of plausible, but and that's why I kind of I prefer to stick to more algorithmic view on that. So consider this only as communication channels on which you propagate the this G stuff. Yes, I should stop talking now. I just want to show you one interesting thing. It was by chance I discovered that it was created by basically people from my own university, and it's a variant of self-organizing maps, elastic maps, elastic map. That's a different approach. So, well, different but similar at the same time. So please have a look. I think it's interesting. So it is created assuming based on physics law. Physics law. So these nodes over here. So they treated not as communication channels, but rather as resistance, physical resistance. And so as part of the training process, you basically change the resistance. And as such, you kind of you stretch your surface, in different directions. Again, I will not stop. I will not go into details of it, but I think it's kind of interesting concept in itself to look at. Now I stop this class. You will discover. You will try self-organizing maps yourself in Lab 4. Try the vectors that you get from Lab 3 to visualize. And maybe you can use the same configuration as from the paper, like 16, I think it was like 16 by 16 lattice, and see how languages are arranged. So you will see clear patterns like Baltic languages, clustered together, Western Slavic languages clustered together, Scandinavian. So that is quite cool. Yes. All right, so that's it for today, and I think you two are least lucky ones. So basically, so let me stop recording and.